Welcome, fine physics folk. Today we are really going to get into the idea of conservation of energy. Up until now, we've only been getting a peripheral look at conservation of energy. We haven't really dived deep into the subject, and that's what I wanted to get into today. The law of conservation of energy, as I've said before, is the most fundamental law of all sciences. It has to do with the fact that energy is not created or destroyed, it is merely transferred between forms. So last week, some of you spent minutes, some of you spent hours and hours and hours on the Jason roller coaster. And regardless of your level of success, I hope that you were able to kind of notice a few things about the simulation, particularly this bar right here. The PE, KE, DE bar. I hope we know that potential energy is the energy of location, of position, of how high it is relative to the ground. The KE bar was the energy of motion, how fast it was going. And the DE bar, for those of you who actually read the descriptions, that meant dissipated energy, or the energy that was lost to heat, friction, essentially all other energies that are not potential and kinetic. If you noticed, when you started the simulation, this bar was mostly empty. As you went up your first hill, you saw that your PE bar was getting bigger. What happened was the roller coaster's chain was doing work to the roller coaster. And because it was doing work to the roller coaster, the chain was giving it energy. Where did that energy come from? It didn't just create energy. The chain is run by an electric motor. So the electric motor's energy is getting transferred to the chain, which then transfers it to the roller coaster. Once the roller coaster was off that first hill, off the chain, all the energy did was convert back and forth between the other forms, potential and kinetic. And over time, friction and heat would kind of eat away at the energy that the roller coaster had. But let's just pretend that, let's not worry about friction and heat. Let's just say all the roller coaster would do was go back and forth between potential and kinetic energy. You saw this to a degree. These bars right here would just get bigger or smaller depending on the speed and the height of the roller coaster. So let's look into this problem. I want you to understand that the total energy in this situation is always the sum of all the other component energies. That's what we said. The law of conservation of energy means the energies simply just transfer back and forth between different types. Now, in a practical sense, we're really not going to get into all those types of energy in our physics class here this year. The types of energy that we are going to get into, though, are going to be potential and kinetic. I know we just did the whole roller coaster thing. We had the dissipated energy. We talked about thermal energy. We talked about all these other types of energy. And in the real world, they are there. And the calculation will work the same with them. You'll just include those into the factor, like you saw on the roller coaster and in the skate park the week before with the guy in the ramp with the bars going up and down, and over time the friction, the thermal energy kept going up. But at any given point in time, if you paused that simulation, all three bars would add up to the total energy. For simplicity, this year, we're just going to look as if there's potential and kinetic energy. But I just want you to know that this works as if you add more energies than just these two. So we have a boulder that's just sitting on top of the cliff. The potential energy is 500 joules. The kinetic energy is 0. It's not moving. It's just sitting at the top of the cliff. So what is the total energy of this boulder? Well, it's the sum of the PE and the KE. So the total energy is going to be 500 joules. Perfect. 500 plus 0 is 500. Easy. Now let's just say that it falls. So this is the same stone at a different point in time. And let's think about it. As it falls, its height is decreasing because it's getting closer to the ground, so it's less high up off the ground. As the height decreases, as an object falls, its speed increases. We know this. We knew this from early in the year when we were dropping things, and as we drop them, the speed, the velocity would increase. So we can see that from the first point to the second point, the kinetic energy has increased. That makes sense. It's going faster. What's going to happen to the PE? Well, the PE is starting at 500, and now it's closer to the ground. We know that the PE has to be less than 500. But specifically, how much? I know that the total energy never changes in a situation. It is merely transferred back and forth between two types. So, if the kinetic energy is 150, the potential energy would have to be 350. I've been practicing my fiddies. So that when you add them up, it equals 500 joules. So you have the same total energy in each circumstance. Okay, what about right here? What about right here where I say now you have 100 joules of potential energy? What's the kinetic energy have to be? I think we're starting to see the pattern here. It's got to add up to 500. So that means the total energy here has to be 500. Okay, what about right here? Right as it's hitting the ground. The moment it hits the ground, not quite, it hasn't hit the ground yet. The kinetic energy would have to be 500 because all the energy has to add up to the total energy. But wait a minute, Bizzuto. When it hits the ground, it doesn't keep moving. You're right. When it hits the ground, it then transfers its 500 joules of energy to the ground. It might make a little hole in the ground, so it did some work to the ground. Or maybe it warms up the grass or the dirt or whatever a little bit. But that energy gets transferred to other forms of energy in other objects. So all we have here is an example of how the energy transfers within one object moving as it falls. We're not talking about transferring between objects. We're just talking about one object transferring between its own two types of energies. So let's think about it. As it falls to the ground, the PE gets lower. That makes sense because as it's falling, the height is decreasing. As it falls to the ground, the KE gets bigger. That makes sense because it's going faster. So another way you could say is that as it falls to the ground, it loses potential energy because it's converting it to kinetic energy. Conservation of energy. But then there's, of course, one more question. What if I wanted the height? What if I wanted the exact height that it fell from? How could I do that? Well, it says it's a 5 kilogram boulder. What energy connects to height? Potential. We have to understand that potential energy connects to height and kinetic energy connects to velocity. So to find the height at the very top, I'm going to take the PE at the very top. And I'm going to plug in all these values. Mass, gravity, height. Plugging that in my calculator. I'm skipping a few steps, but I know you can figure this out. We get a height of 10.2 meters. So we can actually get a lot of information from this. Okay, what if I wanted to know the velocity at this spot right here? What's the velocity right there? Well, to do velocity, we need to use kinetic energy. Ke equals 1/2 mv squared. Okay? Great. The kinetic energy is 400. 1/2. So when we talked about mass earlier in the year, and we talk about how mass changes, if a rock falls to the ground, does the mass change in that circumstance? No, nothing is going into or coming out of that rock. So we're going to have a constant mass in these situations. Nice. 400 equals 2.5 v squared. You divide both sides by 2.5. You get 160 equals v squared. Then when you square root that, you get 12 point, I'm just going to say 12.6. I know there's more decimals, I know. So, all I'm trying to say is this. At 4 different points in time, it's going to have 4 unique heights and 4 unique velocities. Once you know the mass, you can actually puzzle it out and fill in the blanks so that you can figure out how fast it's going and how high it is at any given point in time. Okay, here we go. This is a little bit different, but still doable. Let's look at this one. Let's just say, ultimately, what I want to get is I want the height here, and I want the velocity here. That's what I want. Okay, oh, that's easy. To get the height, I need a potential energy. And to get the velocity, I need a kinetic energy. I don't have either of those. Okay, how can I do this? This is the same ball at 4 different points in time. I'm going to label them. It's the same ball, it's just rolling down a hill. So we know that it's rolling down the hill. The KEs should be increasing as it goes down, and the PEs should be decreasing. So from the few numbers that we see, we have that trend. I want you to get into the habit of being able to jump around and solve a problem in the order that makes sense. You cannot just start from the top and work your way down. I cannot figure out what this blank is first, right here. I need to do something else. How can I get the total energy? I have to find a spot where I have both a PE and a KE. There's only one spot, spot 2. I have a PE and a KE. So if I add those up, that means my total energy is 1200 joules. That means every spot has to add up to 1200 joules. So because I know that every spot has to add up to 1200 joules, I can fill in the blanks. I can fill in the blanks. Every spot has to add up to the same number. It's not so it's not always going to be 1200, it's not always going to be 500, it's going to be a different number for every problem. But once you know what that number is, every spot adds up to that number. Okay, so I found the total energy, and now, bang, right here, got it, love it. So this is how it's going to work. I am going to, it's got a 10 kilogram ball, I'm looking for the height right here, I got to use the PE. PE equals mgh. PE equals 10, 9.8, H, oh, and the PE was 480, whoops, my bad, sorry about that. 480 equals 98H. When you divide, you get about, I'm going to call it 4.9 meters. Nice. So the math shouldn't throw you. Once you know how to get the, once you know how to get the energies, you should be good. Please know that depending on the spot, you're going to use the energies that correspond to that spot. So because I'm looking for the kinetic energy here, I have to use the kinetic energy that corresponds to the spot, which is, in this case, 100. Excuse me, 1,000. Wow, I'm a little, ooh. 1/2, 10, v squared. Half of 10 is 5, 1,000 equals 5 v squared. Divide both sides by 5, 200 equals v squared. And then I square root that junk. And I get 14.1 meters per second. Simple. So how could this get more challenging? When you have to think about a situation. So here, let's just look at this situation. Little Susie's going to take up tightrope walking. So there she is on her tightrope. She's doing what little Susie does. And let's just say that she falls. And here she is falling at 3 different points in time as she's falling to the ground. So what I'm going to do is, we understand how this is going to work. Why am I making these lines bigger? These lines should indicate how fast she's falling. And we know that the longer that she's in the air, she's going to be falling faster. We know that she has a mass of 48 kilograms, okay? So I want to figure out all of these blanks. Well, let's go ahead. Let's go put to the test everything that we've learned. So here she is at rest at the top. Thankfully, I remember my keywords. When I see at rest, I know that the velocity is 0. If the velocity is 0, the KE is 0. So we can't forget the old stuff. Okay, perfect. So what's the PE? PE is mgh. The mass, the gravity. I don't have a height. Huh. I guess I can't solve that yet. That's okay. Let's go to the next one. Here, she is falling 6 meters per second. Love it. With 6 meters per second, that's a velocity. So I know I can solve for a KE. KE equals 1/2 mv squared. So KE equals 1/2 mv squared. 1/2 48. 6 squared. You just type that in your calculator. And you get a kinetic energy of 864 joules. Awesome. But what's the PE? Well, don't know height. Well, let's keep moving. Check another spot. Who knows? Here she is moving 14 meters per second. So we just did this. With 14 meters per second, we can get the KE. So KE, we just plug it in. Plug and chug, my friends. We're plugging, we're chugging. You just type that in your calculator. You should get, indeed, 4704 joules. While, I'm going to go back to reading the question. She was moving 14 meters per second while 7 meters high. Oh, with a height, I can get a PE, because that's just mass times gravity times height, mgh. So that's going to be 48 times 9.8 times 7, 3,292.8. Awesome! Check this out. Because I have both a PE and a KE at the same spot, I can add them up. What students do when they mess this up is they add a PE from one spot to a KE from another spot. You can't do that. So I can't add like the PE from here and the KE from here. They have to be at the same spot. Because I have the PE and the KE at the same spot, I can add them up. And when I do that, I get the total energy. So my total energy is TE equals 7996.8. I believe that's right. Yes, that's good. So that means 7996.8. That means every spot has to add up to that. Every spot has to add up to that. Once you get the total energy, now everything's going to fall into place. So 7996.8 minus 0 is 7996.8. what is this? What is the missing PE here? Well, I'm going to do 7996.8 minus 864, and I'm going to get 7132.8 because these two have to add up to this. So these two add up to this. These two add up to this. These two add up to this. And let's take a wild guess. These last two are going to add up to that as well. So the key here is once you know the total energy, you're good. So it says here she's 2 meters high. Okay, so if I can calculate the PE by doing PE equals mgh, we're good. Multiply that out. That's a 2. Sorry, that's a 2. Bad handwriting. I get a PE of 940.8. And then I'm going to do the 7996.8 minus that answer, and I get a KE of 7,056. So let's think about this. Every point adds up to the same number. Now, as she falls, conceptually, do these numbers make sense? Let's think about this in a conceptual, logical way. She starts with a big PE, and as the PE goes down, every time she's getting close to the ground, that makes sense. The PE goes down, the KE goes up. As one decreases, the other increases. That was the fundamental point of doing the Jason roller coaster last week. I wanted you to see that as one bar decreased, the other bar increased. The energy was just transferring between the two of them. They didn't just appear and disappear. It transferred between types. So we're just starting this, and I'm pretty sure there will be questions. However, I'm here for you. Your assignment this week is going to be to really think about this and do some math, do some thinking, do some concepts, and I'm going to be here for you to help you every step of the way. Join me for office hours if you have thoughts, problems, questions, or concerns, and I will see you guys next time. Be well.